Okay, hello. This is a video discussing the solution to the second step question on assignment 20. The first step question was all about the Fibonacci numbers and proving a relation using induction. There is a video recorded for that. This is the second question, which is actually a step 3 question about this operation delta. So what does it say? So it says delta is an operation which basically takes in, you give it some polynomial, h of x, and it will spit out another polynomial, delta h of x. Okay, and the way it does that is under these 4 rules. Okay, so the first rule is that delta of x is always equal to 1. That's how it's defined. There's this nice summation property. So if you take the sum of the functions, then apply the operator, is the same as taking the operator of the functions individually and then adding them together. We have this a similar idea here, but with a constant, so you can take constants out of the operator. And likewise, there's a rule here for the product of 2 polynomials in terms of this delta. Okay, so the question says, using these rules, show that if f of x is a polynomial of degree 0, which is defined to be a constant, then delta of f of x equals 0. Okay, so I honestly think that this first part of the question is the hardest part, because you have to get used to what this delta operator is really doing, right? It turns out that this operator will be the derivative, but we don't know that at this point, right? Okay. So where would we even start with this? Well, you might have to experiment first. This is the sort of question where you might try a few things and they don't really lead anywhere. And eventually you might stumble across this. Okay, so we'll say let f of x equal 1 and g of x equal 1. Okay, let's see what that gives us. Well, from property 4, right, so I'm going to say explicitly which property I'm using. We end up with delta 1, right, because it's going to be delta of 1 times 1, equals 1 times delta of 1, plus 1 times delta of 1. This is equivalent to saying that delta of 1 equals 2 delta of 1, and that's equivalent to saying that delta of 1 equals 0. Now, obviously, that's not sufficient for what we want to prove. We wanted to prove that the delta of any constant equals 0, but it gives us a starting point, right? This is a fact we didn't know before, and we do now. So at least we've made some progress, right? Well, immediately, let's say, again, let f of x equal 1. From property 3, we know that delta of lambda, right, because this is going to be lambda times 1, equals lambda times delta of 1, which implies that delta of lambda equals, well, delta of 1 equals 0, so lambda times 0 is 0, and so delta of lambda equals 0 for any constant lambda. Okay? So that's proved what we wanted. Okay, that's as desired. Okay, so we've done the first part. It then asks us to calculate delta of x squared and delta of x cubed. Okay, so let's do that. So I would say let f of x equal x and g of x equal x. The reason I'm doing this is because I know what delta of x is, and to get delta of x squared, I know I can just multiply these two things together, and I have got a rule for taking the delta of when you multiply two things together, right? So it seems logical to me that this should be our choice. So this gives us, so maybe I should say, from property 4, this gives us that delta of x times x, so delta of x squared, equals x times delta of x, plus x times delta of x. Delta of x is 1 by definition of property 1 here. So this is x times 1 plus x times 1, and I should say that this is from property 1. And this just equals 2x. Okay, so we end up with delta x squared equals 2x. Okay. We also need to find what delta of x cubed is, right? They've also asked us to find that, what delta of x cubed is. So let's do that. So how would I do this? I would say let f of x equal x, g of x equal x squared, and then literally the same process as before. From property 4, delta of x cubed is going to equal x squared delta x plus x delta x squared. That's x squared times 1 plus x times 2x, right? The fact that it's times 1 is the fact that delta x equals 1 from property 1, and the fact that delta x squared equals 2x, we've just proved. Okay, so this is equal to, so this implies that delta x cubed equals x squared plus 2x squared, which is 3x squared. Okay. At this point, you can probably work out what's going on. We're taking derivatives. Okay, this delta operator is actually the derivative operator. Okay, oh, there you go. That cut off at the bottom there, but that's what I've written. Delta x cubed equals 3x squared. Okay, cool. The next part of the question then, and believe it or not, the last part of the question, basically says that we need to prove that delta of h of x is the derivative, okay? And this actually should be identical, okay? It's always equal to the derivative, okay? How would we do that? Well, it's actually very easy to prove, to be honest. And the way we're going to do it relies on proving one fundamental fact, okay? And that's this. So, conjecture. We're going to need to prove that delta of x to the n equals nx to the n minus 1 for all n greater than or equal to 0. Okay? The reason you might believe this to be true is because, well, it's told you it is the derivative operator. Okay? And so it seems reasonable that, well, we know that the derivative of x to the n is this thing, so this should be true. Okay? How would we prove that? Okay? Well, we only actually need to prove this for all natural numbers, okay? And so we're going to prove it by induction. So remember how I set out the induction last time. I said let P of n be the proposition that delta of x to the n equals nx to the n minus 1, and this is for n greater than or equal to 0. Our base case is n equals 0, where on the left hand side we end up with delta of x to the 0. X to the power of 0 is 1, and that's equal to 0, which is equal to the right hand side, right? So we're done. The reason it equals 0 is that was something we proved initially, right? So P of 0 is true. Okay, I'm just going to go on to the next page for the next part of the induction. So we've done our base case. The next step is to assume that P of k is true. So that's what I'll write. I'll say assume that P of k is true. So what this means is that delta of x to the k is kx to the k minus 1. Our aim is to show that delta of x to the power of k plus 1 equals k plus 1 x to the k. Okay, and we can try and get that from basically using a similar method to what we did for x squared and x cubed. Okay, so I'll say something like let f of x equal I don't know, x to the k. Let g of x equal x. Okay. From property 4, remember property 4 was the one that was the product formula. Okay. So from property 4, we get that delta of x to the k plus 1, right, because it's x to the k times x, equals x to the k times delta of x plus x times delta of x to the k. Yeah. Delta of x is simply 1. Delta of x to the k is equal to k x to the k minus 1 from assumption. And this is equal to x to the k plus k x to the k, which equals k plus 1 x to the k. So p of k plus 1 is true. Okay? Okay, cool. And so now we just write down our conclusion. So we'll say something like, since p of 0 is true, and p of k implies p of k plus 1, then by induction, like that, so then by induction, p of n is true for all natural numbers n greater than or equal to 0. Okay, something like that. Okay, so that's what we've proved. We've proved that. What were we actually after? Well, let's look back at the question. It asked us to prove that delta of h of x equals this for any polynomial h of x. So now what we'll now say is we'll say let h of x be an arbitrary polynomial. Now, if you haven't seen this before, this is a super useful, it's not really a trick, but it's a sort of useful definition, is that we can write an arbitrary polynomial as follows. So I tend to write it as a0 plus a1 times x plus a2 times x squared plus etc. up to an x to the n. Okay, this is a degree n polynomial. Okay, these a0, a1, etc. are just the coefficients of the constant, x squared term, and then an is the coefficient of x to the n. Okay, so this is an arbitrary polynomial. And now we just have to apply the delta operator to both sides and hope that it gives us the derivative. Okay, so what is delta of h of x? Well, just substituting in what h of x is, it's delta of a0 plus a1x plus a2x squared plus etc. up to an x to the n, which equals delta of a0 plus, now I'm going to use property, let's check what number it was, we're going to use property 2, which is this summation property. So that's delta of a0 plus delta of a1x plus delta of a2x squared plus etc. up to delta of an x to the n, and this is using property 2. Again, it does say to state explicitly when you actually use one of these properties, so it is important that we write this down. Well, this can be written as a0 delta 1 plus a1 delta x plus a2 delta x squared plus etc. up to an delta x to the n, and this is using property, let's just check, I think it's property 3, right? Yeah, property 3, we can take constants out, that's all I'm doing here, so we're using property 3. And so this can be written as, well, this is 0 plus a1 plus 2a2x plus etc. up to an x to the n minus 1. And this is using claim proved by induction. Okay, so this is what we've proved, is that you can take the delta of x to the n is just nx to the n minus 1, but you can just say that this is the derivative of h of x with respect to x. Okay, and so we're done. So that was the entire question. So notice that it took me, what, like 15 minutes to do this question? Now, of course, I was able to do it quicker because I had already sort of played around and discovered this relationship here. So once you've sort of worked with the operation a little bit, it's actually quite an easy question. It's just this initial step of working out what we're actually doing, which is the hard part, in my opinion. Okay, so that's it for this question. I don't think I've got anything else to say for it. If this was your first step 3 question, hopefully it shows you that, you know, step 3 is maybe not as intimidating as it might first seem. Okay, thank you.